We will continue with the section on artifacts. In fact, I explored in depth a bit into the topic of artifacts and started gathering some additional details and information, especially regarding the screening of radiographic films. We have temporarily delayed some aspects of it, but we are taking some more specifically detailed information as we work, because there are many various artifacts, such as the chemicals used, the developer, and the fixer. However, we can concentrate our attention a little on the digital or computer radiography and digital radiography. In fact, the existing artifacts, if I were to ask what an artifact is or what causes the artifact, if I talk about the term artifact, it applies not only to CT, X-ray, ultrasound, or MRI. The issue is not limited to X-ray or CT or any specific imaging modality. The whole idea is that I receive the signal with my detector, and this signal is not correct. It is significantly deviated from its true value. For instance, if you are imaging a certain object, let's say I have an X-ray tube, and there is a specific leg being imaged, and there is a set of imaging, 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 and there is a set of imaging. This is a highly used user, as it will utilize many formats to clarify that the image receptor will provide uses. The intensity of transmitted radiation will appear if the intensity value is the intensity of transmitted radiation if the intensity value is the intensity of transmitted radiation if the intensity value is the intensity of transmitted radiation if the intensity value is the intensity of transmitted radiation if 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 the intensity of. Here they are below black, and the higher your density increases, the brighter it will appear. Right, okay? Yes. What does it mean when something creates an artifact? The part I am working on, this signal that came to me, did not come through correctly. There was a problem. What caused this problem? It could be that the patient moved during the exposure time, even if it was for a short period. I am talking about a fraction of a second in imaging, so the movement can occur. This movement will affect the intensity, which is the transmitted intensity that was supposed to reach my image receptor and should have a specific value. However, during the movement, what happened is that the absorption that was supposed to occur did not happen. It experienced a reduction, and its ratio decreased or changed from its true value. In this case, the signal that will appear here will not be a true signal. For example, if I have a specific pixel or a pixel present in the detector and I want to detect this signal, the signal coming to me here has a certain intensity. This intensity might be different in the presence of the object, and when that object moves, it's as if it has shifted. So what is the reason? The intensity here is no longer true. The true value is not achieved, for example, if I am imaging a shoulder joint or a joint examination where I want the margin of the bone to appear accurately or specifically. As a result of this movement, the signal I receive or the transmitted photon will be an average, a summation of two signals divided by 2, meaning its value is not the true value that should come out. Therefore, neither the borders nor my margins are very sharp or smooth, and the resolution has decreased. This is an example of how this happens. For instance, when I thought about the sources of artifacts, I found that I have patient-related artifacts, which could be related to the individual, and there could also be artifacts related to the imaging process itself. While I am imaging, I consider my acquisition parameters using high MA, high KV, low MA, low KV. Is my technique correct in the imaging process itself? Is my SID correct? Is my collimation set properly for the region, or is there a change? This is an imaging or acquisition parameter, and I am working on it. This is imaging for the patient. There could be a problem with movement or tilt. There are no programs, for example, there are no programs with X-ray. All these things can affect me and cause artifacts. There are artifacts related to the patient, such as motion artifacts and processes like lapsing or fixation. If there is something present, all of this will create artifacts and change the value that should come to me, as well as the value of the transmitted photons that should come to me. Now, regarding the patient and the imaging, the reading process or the process related to the detector itself, for example, what is the idea of the CR? It is that I bring the cassette and take pictures of the patient after I get my cassette. What do I do after that? I perform a reading, place it in its reader, and start from this cassette. It begins to lower the imaging plate onto a specific roll, and this roll starts to burn the imaging plate. Then the laser is directed to scan my imaging plate, and electrons are released. Remember the topic of the F center? The electrons drop to the valence band, producing light photons that represent your signal. Now, if this roll is not clean, will it affect the results? Yes, it will. If the roll itself has a problem, like being slow, for example, if it slows down in the middle of the film while I am scanning, then a part of the film will be exposed to a higher laser intensity. Consequently, the light intensity that comes out will be higher, resulting in a brighter part compared to a darker part. These are three of the main sources that I will talk about. The main sources are the four that exist, but I will discuss the categories that I will divide for you. The main sources that I will talk about. The main sources that I will talk about. For example, lumbar spine lateral and shoulder joint, and it is evident that this motion causes artifacts in the images present. This motion is related, of course, to the artifacts present. There may be a procedural factor, or it may be imaged with keys like Nicholas and so on. All of this can cause artifacts and lead to distortion in the existing signal, and such as there are things related to image acquisition artifact. 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 There are things related to image acquisition artifacts. There are things related to image acquisition artifacts. Or I came at this time and got my cassette. Imagine that my radiographer forgot to do a reading and set it aside. Another technician or the same radiographer took my cassette and took another image. What happens is that you will end up with two images overlapping, meaning now you have two images that have been created here. In this view, you have here, for example, this is an image of the valve, but there is another image present that acts as a background for it. I refer to it as if it has been captured twice. The same applies here. For example, this image also shows that it is very likely to happen. The reason for this could be that I have the technician working who starts pressing the switch to give exposure. For instance, he tells the patient to take a breath, so he gives exposure. And then immediately after the patient has taken a breath, he presses again. Now, I have a problem here because if this patient is like the artifact that is clearly visible here, this patient has a double G here. So the double G appears in the image as if there are two double Gs present. As for the justification for me regarding this, it should be the true image, as if this is the result of what happened, and this should not occur. The exposure that happened from this should not happen. There are also situations that can occur, for example, while I am taking images or while the technician is imaging, there might be a cassette, El Cassette, that has pain or something on it, and it gets exposed due to a certain reason. So the image that I ended up with, which shows the pain in this way, and I took my cassette and started to image, it turned out that the two images were one after the other and appeared like this. All these are steps in imaging, and there are mistakes related to the individual worker or professional radiographer who is working, such as also the collimation. I know very well that I have, for example, here, there is a filter and a collimator. The collimator has sections in X and Y. This square moves in both X and Y directions. Every metro consists of 4 sections in the X and Y axis. It means it is structured in this way. This square is called the shutter. It moves in the X direction. And this one, for example, moves in the Y direction. They determine the field size and are connected to a regular lamp with normal light during the adjustment process, which is supposed to set the field size based on that light. If the collimation process is not correct, the image will appear in this way, resulting in inhomogeneity in the X-ray beam, where one part appears with more brightness than another part. In contrast, this image shows well collimation. All of this can happen, and among the things that might occur is that I took a picture and then left my image receptor unattended for a while. Value of lives is vague. As a result of leaving the image receptor for a period, we know what happens. If I have an X-ray, I know well what occurs. It's like I have an example of my own. I know very well the leak. This is my design set. When exposed to X-ray, as we mentioned earlier, bromine iodide exists, and with it, electrons appear, showing trapping in the trapping centers within the PSP. Then, the photostimulable process occurs. Right. After that, I should insert the cassette into the reader to be exposed to the laser beam, and then this laser gives energy to the electrons, allowing them to rise to the conduction band and then fall back to the valence band. After that, you will find that something called the fading effect occurs. What is this fading effect? It is that over time, these electrons in the trapping center start to return if you wait on the imaging plate and do not read it immediately. About 25% of the imported signal loses from 10 minutes to 8 hours after exposure, right? So the electrons return on their own and start emitting light. But this light, I haven't really benefited from it. It's as if the exposure you were supposed to do is done, and you haven't gained anything from the emitted light photons. When you perform a delayed reading of the imaging, do you think there will be homogeneity in the image that appears here? No, of course not. You will find that the peripheral area here is different in signal from the center area. The center here will be higher and denser than the peripheral area in your image. This is due to something called the fading effect, which tells you that the loss of electrons or the electrons present in the periphery lose their energy faster. Chuna is significantly faster than that found in the lower area in the region. The fact that this topic is allocated is not unclear, but it relates to the idea that there are certain things indicating that this is connected to the internet, where the lower area tends to be higher than the center. This leads to a situation where the number of electrons that have been affected from the beginning is very high, and thus they can return to the area, but the effect is more pronounced at the edges of the area, showing the impact on the preferred area compared to the central area. Here, for example, my cassette, as you can see, has a certain ring or specific circle that indicates that your cassette is either oriented differently or captured in a different way. In reality, this issue depends on the cassette and the manufacturer of the cassette, meaning that each artifact can be related to a specific manufacturer of the cassette since there are different companies. For instance, there is a flower here that I have. Why does it appear this way? This range appeared due to the fact that my cassette was not oriented properly during the imaging process, which gives you an artifact that affects the image. Also, all of this I am still discussing here. It should have happened that you provided during the imaging process a high dose for the hand area and the wrist joint area, so the image appeared darkened, as you can see, or there was underexposure, leading to the appearance of quantum noise or quantum mottling in this way. You need to correct this by increasing your milliampere and adjusting the parameters. All of these are acquisition parameters, and it is preferable that they occur on the machine, especially if I am also talking about screen film radiography. The dynamic range is extremely sensitive to changes in factors such as lighting conditions, sensor sensitivity, and lens quality, unlike digital imaging, where you can manipulate post-processing and enhance the image quality.
This is also what I mentioned before. Sorry about that. I don't understand the slides. Can you explain something else? Okay, fine.
Do you see any artifacts here? Is there something wrong? Is this artifact a result of the cassette itself not being placed correctly? Is everything okay? This artifact is a result of what? It's because the cassette itself is not placed correctly, meaning it's like it's upside down. The cassette itself is not positioned correctly during the imaging process, which leads to the appearance of artifacts. This is due to the construction of the artifact, meaning that this issue does not have a fixed rule. The artifact will not appear in all cases. It relates to the design of the cassette itself, which may include a metallic part, like this one, before radiation, which can create a specific shadow on the film during the imaging process. Here, the quantum noise present is a result of underexposure. This is also clearly underexposure. In screen film radiography, they mention that if there is underexposure, you can increase the milliampere by doubling its value. In this case, you will achieve the diagnostic film you want, especially in screen film radiography. Well, there is something related to the topic of the grid. There is this artifact, the Mori pattern, which is the shape we see as lines, and it is the hypolens present in the image. It appears in the way we see it. This is a grid, and to understand it, its role, how it works, and its types, let's talk about it calmly. First, this is the shape of the cassette, and the supposed part is part of the supposed part is part of the supposed part is 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 the supposed part. So, what does the grid do? If you look at any grid, you will find its type, whether it is linear, focused, parallel, or crossed. You will also find something called strips per cm. When I talk about the grid, I refer to it as high density, which contains a high density part, a radiopaque part, and a radiolucent material part. This is called strips. The function or work that this grid performs relates to the material that contains this text. Right. So I call this what is the function or what does the grid do for me? Honestly, the whole topic is quite simple. The X-ray beam hits the patient and scattered radiation appears. Now I want to reduce the scattered radiation, so I want to use the grid. As I mentioned earlier, the strips in the grid have a specific function. They allow the radiation that is perpendicular to the area to pass through, while the angled radiation is blocked. This means that if the radiation is coming at an angle, I don't want it because it will reduce the contrast in the image. Therefore, we created the grid. As you can see, the scatter reduces the details in the image, decreases the contrast, and diminishes the diagnostic information present in the image. Additionally, it reduces the existing noise. As I said, this is the primary X-ray, and this is the spacing, and these are the lead strips. Now, how many lead strips are there? Remember the number I mentioned regarding the number of line pairs per centimeter? I will repeat the same for the grid. How many strips are there per centimeter? You will find, for example, that there is a grid with 40 to 50 strips, which I call a low frequency grid, and there are those with 50 to 60 I call it media frequency grid from 40 to 50 centimeters. From 50 to 60, I call it media frequency. From 60 to 70, I call it high media frequency grid. You will find this information regarding the type of grid, whether it is linear as we see, or cross, or focus, or anything exactly. It also tells you the SID, which is the distance between the source and the imaging, distance that you should use if you are going to use this grid. I want to point out here that the length of the strip itself is H and the gap is D, which gives me something called grid ratio. What is the grid ratio? It is the relationship between H and D. The smaller the gap, it means that the number of lead strips per cm increases. Isn't it a whole line of beers? I'll say the number of lead strips per centimeter increasing means that I will remove more scattered radiation. However, when I remove more scattered radiation, it will reduce the number of photons coming to me and decrease the number of photons that will reach the imaging plate. So how do we connect this story? It's related to the grid ratio, which is the ratio of H to D. If the grid ratio is high, it means that the gap is small, which means you need to increase the dose to continue achieving the exposure and maintain the exposure you have reached, for example. All right, we will return to this topic now and discuss it in the next slide. Okay, what is the topic of grade frequency? How many strips per cm should I increase? What does this mean? And why do I need to increase it? Why do I use the low frequency grid? Why do I use the medium frequency grid? Why do I use the high frequency grid? I'll tell you something. Let's go back to the grade ratio and finish. You will find that a grade ratio of 5:1 is the reduction ratio that will occur in scatter. The higher the grade ratio, the greater the reduction in scatter will be. However, keep in mind that this will come at the expense of the dose used, which is commonly noted in the table set at 8:1. This reduction in dose will affect the overall dose. The grid used is a common type, and it is fixed on the table, which has a grade ratio of 8:1. There is a remaining value of 16:1, which is exactly 16, right? This is regarding the equipment we are using, okay? I have a slide. I am working with it, okay? Types of grids. We understand that the function of the grid is to remove the scatter present. Can the grid cause artifacts? Of course it can cause artifacts. So what are artifacts? Let's first look at the types of grids. There is a type of grid called parallel. What does parallel mean? It means that these lead strips, as you can see, are parallel to each other. They are all aligned. Therefore, what does this mean? It means that the X-ray beam coming at an angle like this will hit these strips and pass through, even if it is the primary beam. So, what is the solution? I told you I could use this grid, but one of its disadvantages is that if I have a small field of view or a small organ, I can work on a small area or a small organ and image it with this. Its use is that it is inexpensive, meaning its price is low. But the problem is that you will have the area of the edges that are present. What will happen is that everything you have will come into what is available. So I can use it. Use it for what if I am working on something else? If we pay attention here, in the parallel grid, you are essentially removing scatter from one direction, while in the cross grid, it's as if you combined the two, reverse them, and combine them together. The cross grid removes scatter in 2 dimensions. If we assume this is the y direction and this is the x direction, then it has applications. In one direction, assuming this is the direction of the x and this is our direction, this also makes it have various uses.